Good morning, guys. This is our first continuation lecture where we left off last Wednesday, and then everything got crazy. So today is Wednesday, March 18th. I have traveled up north with my crazy crew. I will send you a photo so you can see. So this lecture is actually coming live from me locked in a bedroom at Grandma's house. Hopefully we won't have any interruptions. So we definitely want to get you analyzing NMR spectra, just like the lab students have. I'll be sending you guys our YouTube channel. Lab students already have it for my classes. And again, you can look at any of the lab videos as well. Anytime you want, which is totally great, especially for NMR. The more practice you can get, just like when we did IR spectrum and GC mass spec, the better. So the more practice, the better. So again, you can't see my face, but you've got our lecture guides. You have my manicured fingers for once in my lifetime, which is kind of funny. And let's pick up where we left off. So last Wednesday, you guys were doing really great at figuring out how many signals we should see on an NMR spectrum. And so here's our little spectrum here. Okay, and then I said, okay, well, looking at this molecule right here, you guys said, okay, we should see two signals. So we've got these methyl group of hydrogens there, and then we have this methine hydrogen right here. So we would see two signals on our NMR. So we can see those two signals here. So there's one right here, a little past that too. And then one a lot further downfield, closer to the 6. Gee, I wonder why that is. Probably because this little methine hydrogen is so de-shielded next to those very electronegative chlorines. Chlorine is fairly electronegative, right? It's just one period lower on the periodic table, with fluorine being the biggest piggy. So fluorine and chlorine, very electronegative. And there's two, so that poor little hydrogen there is stripped bare, very stuck to the NMR magnet, takes a ton of energy. Remember, this number here is reflecting energy. It's proportional to the energy needed to spin flip, to have that beta spin state being anti to the NMR magnet. So anyways, there are our two signals. Now, when you zoom in, which they have done for you there, so they're saying this signal right here, and just match up the chemical shift, is this one. This has been split into two peaks. Okay, and I'll draw these lines up. I've tried to kind of bold in what the computer draws in, so you're really counting those skinny lines there. And what we see is two lines, and we call this a doublet. Okay, so again, these are the same thing. This is zoomed in. Okay, and then something unique is right here, which is nice, is they're giving you the integration of that signal there, and that number there corresponds to how many hydrogens are actually giving that signal. So they're saying 3 hydrogens. So we've got 3 hydrogens. Their signal is a doublet. So 3 hydrogens have a doublet. And we're going to figure out what a doublet means in just a little bit. Okay, lab students already have a head start on that. And then this signal right here, super messy. That's why it's zoomed in, because these are real-time spectra. So over here, you can count the little lines. We've got 1, 2, 3, 4. This is what we call a quartet. So the hydrogen that is really downfield, okay, is being de-shielded. That one hydrogen, and there's that one hydrogen, has a quartet for its signal. And again, this is near the 2 chlorines. Okay, this signal up here is more upfield. This is furthest from the chlorines. Now, some people go, well, I thought alkyl groups are mainly closer to 1. Well, remember, these guys are not too far from 2 chlorines. It's just on the adjacent carbon right there. So they have actually been de-shielded just a little bit more than their normal area, where this would just be, you know, hydrogens. They're near a bunch of other alkyl groups like CH2, CH2, CH3 would all kind of be in this area. But because these guys are right next to two chlorines, it's kind of shifted them a little bit further downfield. So it's really important that we're looking at what's happening to our signals, okay? The splitting pattern. So signals can split. We filled this in last week. And we're going to learn why. We haven't learned why they split in lab. We've just learned on how to read the spectrum and what does that splitting pattern tell us. But why is that actually splitting? So that question why we're going to answer on the next page is super important in terms of a lecture class where we do a lot of explaining in theory. Okay. So what does that actually mean? Okay. So when I look right here, a hydrogen signal is affected by their adjacent neighbor hydrogens. Okay. So it's called the N+1 splitting rule. Okay, so we're going to use this structure and talk about the splitting pattern on the next page. Okay, so spin, spin, splitting or coupling. It's also called the N+1 rule, where N represents the number of equivalent hydrogen neighbors. And we'll explain a little bit more about that in just a little bit. Excuse me, guys. If you can tell by my voice, I am sick. Nothing super scary, just your modern day cold, so don't panic there. Anyways, I kind of feel like I've been sick all semester long. It's been crazy. So let's redraw this thing again from the previous page that we're analyzing. And again, we've got these guys, and then we have this one hydrogen. That would be our second signal there. Okay. Alrighty. So when we look at our, what we'll call our little green hydrogens here, and when we look at these groups, we can say that these three hydrogens have one equivalent hydrogen neighbor. Now, when we say equivalent, we're not saying equivalent to these guys because clearly they're two different types of hydrogens, but we just have one neighbor and he's unique to himself. If this had been a CH2, we would have said those two hydrogens are equivalent to each other. Okay, so we would have said something like that. And when we look at this guy, we're going to go, okay, he's got three hydrogen neighbors that are equivalent to each other. Okay, so they're all the same type of guy or same type of hydrogen. So looking at these ones, we say these hydrogens have one equivalent neighbor, again, equivalent to itself, not to the other three hydrogens. Okay. So putting that into this rule right here, 1 + 1 = 2, which is a doublet. So these three hydrogens have a doublet for their signal, and that's what you saw on the previous page. Okay, and that's because how of this guy can affect these hydrogens' signal. So why is that? What does this one equivalent neighbor do? How can this one neighbor affect the methyl hydrogens? Okay, so how can this one neighbor affect the methyl hydrogens? Remember, our hydrogens are spinning nuclei that behave as tiny little magnets, and we'd already talked about the spin state. So how can this one neighbor affect those three hydrogens? Well, that one little methine hydrogen, he can have a spin up, okay? And he can also have a spin down. Okay? So those are the only combinations that that one little hydrogen neighbor can do. So that means it can affect our methyl hydrogens two different ways. So two different spin combinations that will affect our methyl hydrogens. Okay. All right. So now that's why we're seeing a doublet. Okay. That's where that 2 is coming from, for the 2 different combinations that methine hydrogen can do, to affect our methyl hydrogens. Okay. So now let's take a peek at this one little methine hydrogen. Okay. So this hydrogen has, looking at our structure, looking at the adjacent carbon, the atom directly attached to this one, it's got 3 equivalent hydrogens on it. So this little guy, our methine hydrogen, has 3 equivalent hydrogen neighbors. Okay, so this hydrogen has 3 equivalent hydrogen neighbors. So if I do that n+1 rule, 3 plus 1 equals 4. A 4 is a quartet. And that's what we saw on the previous page. That signal that was downfield was a quartet, meaning that hydrogen has 3 equivalent neighbors. Okay? And typically 3 equivalent neighbors is always a CH3 group. Really difficult to give an equivalent environment if you're breaking those 3 hydrogens up. Okay, so this hydrogen has 3 equivalent neighbors, and that's why we're seeing that downfield quartet. Okay, so in terms of those 3 equivalent neighbors, how can our methyl hydrogens affect, how can our methyl hydrogens affect our methine hydrogen? So remember to review on a previous page in this packet from last week, we talked about the names for the methyl, the methylene, and the methine hydrogens. Well, there are 3 methyl hydrogens, so we've got to think of all of the spin combinations that they could do. So for example, they could all be spinning up. That would be one set of combinations for our 3 methyl hydrogen neighbors. One could spin up, one could spin down, and the third one could spin up. That's another combination. One could spin up, one could spin down, and the last one could spin down. It's another combination. Now the only other combination we could do would be all spinning down. So this are the 4 ways, right? These are the 4 combinations. So the 4 spin combos that will affect our methine hydrogen. Okay? So that's why we're seeing 1, 2, 3, 4. Okay? That's why we're seeing a quartet for our little methine hydrogen here. Okay, so that's where that spin splitting is actually coming from. And then the next few pages, you guys are going to see, various splitting patterns, and then we're going to start analyzing in a different video, like we've done in lab, some actual spectrum. Okay. So the next page you have in your packet is this one here. Just kind of not a whole lot we're going to talk about here, but again, what is a neighbor? Okay, so I've defined neighbor as, looking at your adjacent atom that's attached to whether it's a carbon or an oxygen or a nitrogen. So you're just looking one atom over. Okay, so the hydrogen on this carbon, its neighbor is the adjacent carbon, or again, that could have been an oxygen or a nitrogen, and we're looking at how many hydrogens are on it. So these guys are neighbors here. These 2 hydrogens here are not neighbors, okay, because they're not on adjacent carbon atoms. So this carbon right here is adjacent to this one. And this carbon is adjacent to this one, but these two outer carbons are not neighbors to each other. Okay? And then again, we're not doing any alkenes or alkynes in our NMR analysis. The only double bonds you will see are carbonyl C double bond O's from our different functional groups like aldehydes, ketones, and esters. Okay. Now this is an important little rule. So two different molecules that both have just one signal. Okay. So looking at my unique sets of hydrogen, okay, these three hydrogens are all equivalent to each other. We look at the neighboring atom, there's no hydrogens. So we would say these hydrogens have 0 neighbors. Remember 0, I like to always use the word equivalent because we're going to see where unequivalency comes into play later. So these hydrogens have 0 equivalent neighbors. They simply have no neighbors. So 0 plus 1 would give us a singlet. So that's what you would see. Probably, again, the chemical shift for halogens could range anywhere from 2-ish to 5-ish. And then if there's multiple halogens that are very electronegative, like we saw the chlorines, we saw that signal getting shifted farther down to 6. But again, your job last week, remember over the weekend, you're supposed to slowly memorize that chart of chemical shifts. That's going to be important because you'll probably have some quiz coming up pretty soon online with splitting patterns and chemical shifts, and then eventually building up to analyzing spectrums. Now right here, if we were labeling our signals, look at the beautiful symmetry of this molecule. We don't have 2 signals for this molecule. There's only one signal because these methylene hydrogens, that CH2, is the same as this one. So again, these guys are the same. Okay, so I'm just going to circle it once, okay, because these ones are the same. So they're like identical twins, you could say. So these two are the same as these two, exact same behavior because they have the exact same environment. So they are not going to affect each other in any way. So that's what this statement is saying. It's saying equivalent protons do not split each other's signal. Okay? These are equivalent protons, equivalent hydrogens. So they're not going to affect each other in any way. So these are the same, no effect on each other's splitting. Okay. So when I look at this, I say these hydrogens have 0 equivalent neighbors because they have identical twins next door. Okay? So 0 plus 1, you would see a singlet for the splitting pattern for these 2 hydrogens. Okay? And then these also have the same exact singlet on the same exact spot on your spectrum. So that's something important. When you see not very many signals on a spectrum, but you're dealing with a lot of hydrogens, it usually means there's some sort of symmetry in that molecule, and this looks very symmetrical. So looking at this next one right here, there are 2 signals on this spectrum. So again, we've got these outer methylene hydrogens, those 4 there, and they're all the same. That's why they're labeled B. So we're seeing 2 signals. And then we have these guys in the middle. So let's analyze this. Since we're given the structure, let's analyze it and then see if it matches to the splitting patterns that we're seeing. And then eventually our goal is we'll just have our splitting patterns, and then we're going to deduce our actual chemical structure. It's very important that you are reading everything clearly, okay? You can't go, oh, look, there's 4 signals in this molecule. There are not 4 signals. They will zoom in because often these real-time signals are very kind of messy and unclear, okay? So this is actually real spectrums from a chemical database. And then they have the zoomed in structure. So you've got to read your axes. Okay, this signal right here that, gosh, I can't really count the splitting pattern very well. is right around 2. Well, there's that 2-ish region here. And here I can easily count my splitting pattern, okay? So if you count the skinny little lines, we've got 1, 2, 3, 4, 5. 5 is a quintet, okay? Which means these hydrogens have, well, what would give us a quintet for 5? That n+1 rule. A quintet would be 4 plus 1. So the hydrogens that are giving this signal have 4 equivalent neighbors. The only way to get 4 equivalent neighbors, you couldn't think of combinations like a CH3 and a CH. Those would never be equivalent to each other, but 2 CH2 groups would be 4 equivalent neighbors. Okay, so it's important that you start thinking of how hydrogens are attached to carbons: CH3 groups, CH2 groups, and CH groups. Okay. All right, this splitting pattern right here, we can count 1, 2, 3, and this is a triplet. And what does a triplet mean? Well, to get a triplet, right, a triplet would be 2 plus 1 equals 3, that n+1 splitting rule. So the hydrogens that are giving this signal right here that's between 3 and 4, these hydrogens have 2 equivalent hydrogen neighbors. And again, this is between 3 and 4. This is between 3 and 4, giving the hydrogens that are giving this signal. And the hydrogens that are giving this particular signal have 2 equivalent hydrogen neighbors. The only way to get 2 equivalent hydrogen neighbors is a CH2 group, usually, or you could have maybe 2 CH groups, 2 methine groups, but they would have to be an equivalent environment. So let's see how this sort of matches up, our quintet and our triplet. Our quintet is more upfield in that 2-ish region, and our triplet is a little bit more downfield, okay, in that 3 to 4 region. So we have our structure here. So let's look at these guys right here in the middle first, and we're going to count their neighbors. So this carbon is attached to a carbon here, that's a neighbor, and attached to a carbon here, which is also a neighbor. Okay? So these hydrogens, I always like to start with that statement so I know what I'm talking about, who specifically I'm talking about. So these 2 hydrogens right here have 1, 2, 3, 4, have 4 equivalent hydrogen neighbors. Again, instead of writing equivalent and neighbors out, the really long words, I'm abbreviating there. And it's important to use that word equivalent because those 2 plus 2, those total of 4 hydrogens there, our B hydrogens, are equivalent to each other. If that was a chlorine, then those 4 hydrogens would not be equivalent to each other. So it's really important to use that word, okay? So these hydrogens right there have 4 equivalent neighbors. So that's why we are seeing a quintet. 4 plus 1 is 5 for A hydrogens. Now our quintet should be more upfield. And again, we're supposed to know what those words mean. Upfield means further away from the electronegative atoms, which that guy smushed in the middle, they are furthest away from those 2 bromines there. Okay, now our B hydrogens. And again, I just have to look at one side because these are the same. Those 2 B hydrogens right here have 2 equivalent neighbors. So that's why 2 plus 1 is 3. We are seeing a triplet. We're seeing a triplet for these B hydrogens, a little more downfield. Because they're attached to the carbon that's got the bromine on them there. So our splitting pattern matches just lovely, okay? So let's flip. We're having a ball at Grandma's house. Yep, I'm sitting on the floor. You can see the carpet right there. We've got a bigger structure here. And it says, can you explain the splitting patterns? Now, you might be freaking out, going, oh my gosh, look at all of these things. But remember, some of these things are zoomed in here, okay? So we're going to look at our structure, and then we'll go back to this one right here. Okay, so kind of counting some of these things right here. We've got 1, 2, 3. We can see a triplet here. Okay, so that little 3 is actually supposed to be over here for our little triplet. So I'm gonna put that right there. Okay, so 3 hydrogens have a triplet. Okay? And then you want to start thinking about, okay, what is a triplet? Okay, now right here we've got 1, 2 little lines drawn up from the integration. Okay, so and that number 6 is right here, is applying to this one right here. Notice how tall it is because it's representing a larger group of hydrogens. And remember, a good way to get 6 hydrogens would be 2 methyl groups, a CH3 and a CH3. That would be a total of 6 hydrogens as long as they have the same environment. So 1, 2, that's a doublet. So 6 hydrogens have a doublet. And we want to think about, what does a doublet mean? And we'll go back and label that in just a little bit. Okay, and now this signal right here is kind of interesting. You may or may not be able to count the little lines, and that's okay. You don't need to when it's labeled a multiplet. So sometimes multiplets will be messy, and sometimes they will be clear. So multiplets can both be messy or clear, okay? But if it's labeled as a multiplet, that's going to be something that's very, very important. Okay? A multiplet means that the hydrogens that have a multiplet signal, they have unequivalent neighbors. So hydrogens that have unequivalent neighbors, neighbors that have a different environment, so hydrogens that have unequivalent neighbors, so hydrogens that have unequivalent neighbors will give rise to a multiplet signal. That's because those unequivalent neighbors are different. So they're going to have different effects on a set of hydrogens, which can cause, some sort of messy splitting pattern. Sometimes it's clear. But if I label it for you as a multiplet, that's telling you that the neighbors need to be different. It's kind of like I have 2 different neighbors on either side of my house. I've got the neighbors to the left, and they are super friendly, and they make us really happy. And then we've got our neighbors on the right side of us, and they're not so friendly, and they make us a bit more cranky. So those are different effects that they're having on my household, which is kind of funny. It'll be really funny if they actually watch this video. But anyways, multiplets tell us a lot. So whether you're like, oh my gosh, I need a magnifying glass, whether you can count it or not, okay, is not important. So you can kind of count it, but don't rely on that if it's a multiplet, okay? So you can kind of see the little lines here, 1, 2, 3, 4, 5, 6, okay? So it kind of maybe looks like that, but again, maybe not. So I'm just going to hold off on that. The important part is that it's telling us we've got unequivalent neighbors. Okay, so try not to count multiplets too much because it might throw you off a little bit here. Okay, so the next one we've got here would be this one. And again, you have your packets at home, so you can zoom in. Remember, you can download your well, lab packets online. If you need an extra one of these, I can scan it to you and put it on Canvas. Okay, so this next one here, if you get close, that looks like a triplet. Okay, so we've got 1, 2, 3 lines, and it kind of has that 1 to 3 to 1 sort of ratio. A doublet, the lines are more equivalent in height like they are right here. So these 2 hydrogens have a, oops, a doublet on my mind, have a triplet. And we want to think, what does a triplet mean? Alrighty. And this was our multiplet. Okay. Don't get thrown off here. I had to think for a second here. And I was looking at the chemical shift. This is 1.1 to 1.3 parts per million. So if some people had a hard time looking at this shift right here, there's the 1. So this is 1.3, around 1.3 parts per million. That's this one right here. They just zoomed in on it for you. And they put it further down there, but that's okay. Okay, so this is the zoomed in version. You just need to read your chemical shifts there. And then we've got sort of a messy signal down there. Really hard to see that one, but that's okay because guess what? It's zoomed in right over here. For a second, I was like, oh my gosh, I can't read that. Is something wrong? And then I just looked to the left of my screen because I couldn't see it in my video right here. There's that 4.8 to 5. Well, guess what? That's that region right here. So this one hydrogen, our one hydrogen has a, well, let's count what this is. 1, 2, 3, 4, 5, 6, 7. 7 is called a septet. Okay, so one hydrogen has a septet, and I want you to think, what can this possibly mean? Okay, all right, so now we're going to go back and label what does the splitting pattern mean. So septet was 7. How do we get the number 7? Okay, in terms of neighbors, it's always the n plus 1 rule. Okay, so what does a septet mean? It means you have 6 equivalent neighbors, because 6 plus 1 is 7. Okay, moving back this way. What does a triplet mean? We've seen a triplet before. So this triplet, that means you have 2 equivalent neighbors. Okay, we talked about what a multiplet means. A doublet, what does a doublet mean? It means you have 1 equivalent neighbor, because 1 plus 1 gives you 2. And then again, another triplet, have 2 equivalent neighbors. Excuse me, guys. We'll probably be signing out in just a little bit. So people go, what about this signal here? So remember, this is just your solvent, the TMS signal. That's at 0. So we don't have anything referenced at 0. So let's check this out right here of our ester. Okay. Alrighty. So let's start with A, since we're kind of really upfield here, furthest away from our electronegative atoms. Right. This is upfield. And check out our splitting pattern. So these hydrogens right here, they have 2 equivalent neighbors. So 2 plus 1 would be our triplet. Okay, do we have a triplet that's upfield? Guess what? Yay, we do. We've got that triplet upfield. So that is our 3 hydrogens that have 2 equivalent neighbors. And that's what we're seeing right here. These 3 hydrogens have 2 equivalent neighbors. Okay, so those would be our A hydrogens right here. These are our A hydrogens. All right, let's look at our little C guys right here. I'll switch to a different color. Those 2 hydrogens, let's count their neighbors, have 3 hydrogens to the left. They have 2 hydrogens to the right. Those are different types of hydrogens. That's a CH3, and then we've got a CH2 that's next to a carbonyl. We have unequivalent neighbors. So these ones have unequivalent neighbors. What does that mean? It means these 2 hydrogens would have a multiplet. Okay, so 5 plus 1 would be 6, which is a sextet. Now, sometimes with a multiplet, you can't easily count that, and I don't think we did very well. But again, there's that multiplet that we're seeing for those C hydrogens. Let me see if I can count it. 1, 2, 3, 4, 5, 6. Yep, I can count that pretty good. That does look like a sextet, but the important part, it's not a normal sextet. It's a sextet multiplet, okay? So this one right here is called a sextet multiplet. Got to use the word multiplet because that's telling you you have 5 unequivalent neighbors. Okay? Now here's a really important one right here. Our D hydrogens right here, these guys are next to a carbonyl. That's that important region that we talked about on your chemical shifts. It's kind of like on an IR. We're like, oh, 1700 for a wave number is a carbonyl. Well, hydrogens that are adjacent to a carbonyl, their chemical shifts right around 2, 2.1, 2.2, which we should be seeing on our spectrum. And these guys have 2 equivalent neighbors, so they would be a triplet. And again, that would be right around 2 parts per million because we're adjacent to a carbonyl. Let's check for that triplet. Yay, there we have it. 2 hydrogens that have 2 equivalent neighbors, giving that triplet. That's what we have here. 2 hydrogens that have 2 equivalent hydrogen neighbors. Right? And of course, that region a little bit past the 2-ish number there. Okay. All right, so we're almost done looking at this one here. We've got 2 more sets. And did I label that one? Okay, these are my Ds. Okay. Right in here, we've got 1 hydrogen. It's attached to this carbon that's got a methyl group branching off here and another methyl group branching off there. Again, this is drawn condensed, so if you need to, make sure you draw it out and can see your bonds. So that hydrogen there has 6 equivalent neighbors. 6 plus 1 would be our septet. Okay, now this little hydrogen is right coming off of, well, not coming off of, but adjacent to an electronegative oxygen. So that electronegative oxygen area is kind of in, around 4-ish on your chemical shifts. And we do have a septet in our 4-ish region, right between 4 and 5 right there. We have 1 hydrogen that has 6 equivalent neighbors. So that was that septet that we're seeing that's more downfield. Because that little hydrogen is very exposed to the magnet. It's been deshielded by that oxygen. And then lastly, we've got our, and let me label it, sorry. So this was our E. Okay. And then we have our B hydrogens. So these guys right here are the same. And we look at their neighbor, which is this carbon here, and it only has 1 hydrogen on it. So 1 plus 1 is 2. These hydrogens have a doublet because they have 1 equivalent neighbor. Okay, so where is that doublet? And again, these guys are branching. They're further away from the electronegative oxygen. So we do have that doublet here. And that was our B hydrogens right there. So 6 hydrogens that have 1 equivalent neighbor. So how do we get 6 equivalent hydrogens? Typically 2 methyl groups branching off of another carbon. And then you could throw a hydrogen on it for its 1 equivalent neighbor. Alrighty. So on your own, I want you to, in the leisure of your home quarantine, analyze this one. Notice this one's slightly different. We mentioned this would come up before. These 2 CH2 groups are not the same because this one's next to a chlorine, this one's next to an iodine. Okay, so I want you to take the time to analyze that on your own. Okay. Something I do want to point out in this video here, okay, would be the difference between a quartet, which is 1, 2, 3, 4 peaks, but different ratios. This is our standard quartet. A quartet, that n+1 rule, means you have 3 equivalent neighbors. Okay, so for example, if we have something like this, we would say these guys have 3 equivalent neighbors. So that would be a quartet that we would see for these ones right here. Then there's something that you can also count as 4 peaks, 1, 2, 3, 4. This is called a doublet of doublets. I love how that sounds, and this is a type of multiplet. So this right here is a multiplet. And what does a multiplet mean again? It means unequivalent neighbors. Okay, so unequivalent neighbors. And the ratio is different. These are all the same height. Okay, so let me show you how we might get a doublet of doublets for something. Okay, so let's do this. Okay, so let's say these 2 hydrogens had a doublet of doublets. Well, how are they going to get something like that? They've got to have 1 hydrogen neighbor, because 1 + 1 would give you a doublet. And then let's just branch some things off of here. Let's say, I'll just kind of do something like that. Okay. So far, these 2 hydrogens have 1 neighbor, and 1 + 1 would give a doublet. But again, we've got to finish our molecule here. I'm going to do it in a different color. Okay. So, looking at these guys right here, we can't say they have 2 equivalent neighbors because these 2 hydrogens are different from one another. So what happens in the splitting is this 1 hydrogen, right, can affect these guys 2 ways. It could spin up and spin down, right? Thinking about our spin combinations. Now, these green hydrogens, this little methine hydrogen here, how can it affect this guy? Well, it could spin up and spin down, also affecting these 2 methylene hydrogens 2 ways. So we've got 2 effects here. We've got 2 effects here. So that's why you're seeing 2 + 2 is 4. But it's all the same height. Okay, so these hydrogens right here would have a doublet of doublets. Okay, so it's important to know where a doublet of doublet comes from. It's from having 2 unequivalent neighbors. So kind of a neat little splitting pattern there. So again, some more that I want you to take the time to analyze their splitting pattern. Now again, these are nice because they're giving you the number of hydrogens that are having this particular signal. Okay, right here. Again, this one's zoomed in right there, so you can easily count and see that it's a quartet. And this one's easy to see the triplet. Okay, now this big messiness here, it's a multiplet. It's saying 5 hydrogens have this little multiplet here, and it's really, really messy. Okay. Now, that's okay. What's important is this. I want to pay attention to our chemical chefs. This 7 region tells you you have an aromatic. Aromatic hydrogens are always in the 7-ish region. Okay. Now, they do have them labeled different. Okay. Because those hydrogens themselves are not all equivalent to each other because you have something branching off of here. But because all of these hydrogens are on the same aromatic molecule and all pop up right here, everything gets overlapped. So it looks really, really messy. So it's okay to look messy. Okay. The 7 tells you it's an aromatic molecule. That's the important part. The multiplet tells you that some of those hydrogens have unequivalent neighbors. Okay, so what exactly is everything that's being smushed in this area right here? Well, let's look. This little guy right here, our E hydrogen, he's got 2 equivalent neighbors. So 2 plus 1 is 3. He would have a triplet. Okay. Now, our D hydrogens, okay, they've got different types of neighbors. He's got a C neighbor to the right and an E neighbor to the left. Okay. Our D hydrogens would be our doublet of doublets, which is a multiplet, telling us we have unequivalent neighbors. And then finally, our little C hydrogens here, okay, they have 1 equivalent neighbor. Right? Just looking, I've got 1 neighbor over here. There's no hydrogens right here. So 1 plus 1, this guy would be a doublet. So you have all of these things. You have all of these things that are all smushed right there. And that's why sometimes, again, you can't read it, and that's okay. It's the number that's really important. Or also if you had your degrees of unsaturation, that would be great. And then these ones are really easy to read right here. Further upfield, right, in our alkyl region, you can see all the way over there. You've got a triplet, and then of course our quartet, which is a little bit further downfield, getting closer to our big electron sink, our slightly electronegative aromatic ring. Okay, so these guys right here have 2 equivalent neighbors, 1, 2, 2 plus 1. This would be our triplet that we're seeing upfield, and then of course these 2 right here would be our quartet. They're 3 plus 1. So 3 neighbors plus 1 is 4, giving a quartet. So those are the signals that you're seeing right there. Almost done, guys. We're doing fantastic, just like as if we were in class today at 11:30 a.m. So it says here, the presence of an electronegative group allows the splitting pattern to differentiate more clearly. What would it look like? So sometimes when there is a very electron withdrawing group, we all know about that nitro group from our previous chapters when we substituted aromatic rings, it helps these different hydrogens, their splitting pattern, to be shown more easily. Now remember, this whole section here should pop up, you know, in that 7 to 8-ish parts per million region. Okay? But I want you to tell me, based on what we did on the previous page, what would you see for these guys? What would be their splitting pattern that you would see based on how many neighbors they have? And for these, and for these. Okay, that's your job. I want you to figure out those 3 signals. And again, they would all be right in here. Of course, you want to think about, out of A, B, and C, who would be closer to 8? Who would be closer to 7? Who's more de-shielded? Who's more shielded? Again, this is very, you know, already de-shielded already, but you've got to place those 3 signals somewhere in here. What would it look like? All right, got to go cough some more. Flip in again. You've got one more page, a little more detailed. We went over a previous one last week, but some people had asked, oh, can I have a really even more detailed one, and that's fine. Just keep in mind we're not doing double bonds for alkenes or triple bonds for alkynes. Okay, the only double bonds you're going to see are in an aromatic ring or a C double bond O. All right, guys, signing off. Nice long video. At least you can hit pause anytime you want to and take breaks. And you will be having a Wiley homework assignment. I'm going to create it later today to get started on NMR. And the next video you will see will us be analyzing our NMR spectrum. Now, you should already have a packet at home. Our second packet, I believe I gave that to you last week, but I can scan another one using CAM scanner on my phone, which a lot of you are going to be using to submit lab materials to me. So I will use that and put blank spectrums on Canvas for you guys to download. So signing out. I will talk to you guys again. Feel free to use the discussion forum on Canvas like we talked about. And you can, of course, keep emailing me. I'm checking a couple of times every day. All right, guys, stay safe. Wash those hands. Bye-bye.